Alright, today I'm going to talk about the very basics of the neural network. As a starter, let me talk about some like primary types of the machine learning, not just neural network. So we can basically talk about supervised learning. And when I say supervised learning, it's about the data set composed of X and Y. And then this supervised learning is forming the most of the machine learning area. And the very simple case of the supervised learning could be a regression problem. Say you have data x 0, 1, 2, and our y data is like 0 0.01, 1.98, and 6.2. And we can instantly know as a human that y is almost 2 times x plus some kind of noise. And using linear regression functions provided by MATLAB or Python, we can just find out this constant for x. So if I graphically represent this, you have x and y at x equals 0, and then x equals 1, x equals 2. We have say y data at there, and y at most 2, 4, 6 is scaled by 2, and it's just 1. We have first y data there, and second y data is about 1.98, so it's slightly lower than 2, and the last one will be 6.2, is slightly above 6, but still we can draw a line, and this is our y equals 2x. That's the basic regression problem, and well, traditional way of regression algorithm will work as well as the neural network. However, when it comes to data like images, say you have an image of a cup, like that, and that is your image 0, and you have another image, say a cat, and that is your image 1. So our X is composed of a bunch of images like this: image 0, image 1, and your Y maybe the actual label like cup, cat, or just for the convenience we can say 0 for cup, we can say 1 for cat. Okay, so and the images are composed of bunch of numbers, and is made of 8-bit unsigned integers. So the value can be between 0 to 255. So say your image size is W, for width and height is H. Your number of data will be W times H, and that is your img0 or your x0. So your x0 has a lot of numbers to process. I mean, we cannot even like draw a point like this because it has so many high dimension. So in this case, we cannot really just use this kind of regression algorithm to classify whether the given image is a cup or cat or someone else's face, and can you, by looking at the face, can you tell the name of the person or something like that. It has been impossible until this convolutional neural network technique comes out. Well, it has been there, but it took for a while to make it actually work in practice. So that was just generally saying the supervised learning, and we hope to go more about the convolutional neural network as we proceed this series. On the other hand, there's also type of machine learning called unsupervised learning. It means you can still sort of train your machine learning algorithm without this kind of Y data. And the k nearest neighbor, the KNN is for k nearest neighbor, is one of the most popular unsupervised learning. So what it does is very simple. In 2 dimensions, say you have distributed data like this. And they have distinctive labels like red and blue. Like this. We don't really know the boundaries of this red and blue, and we don't even have a label. Say your data is coming in as something like this. There's no label. However, we can still sort of cluster this data from left and right or something like that. Since there's no label, we call this grouping problem as clustering problem. And if we have this kind of, say there was a label like this, then it becomes supervised learning, and we call it classification problem, just like this. We have label here. But since we don't have label, we call it clustering problem. And k nearest neighbor is one of them. What it does is iteratively go over the calculation of the mean. So the mean of this can be red and blue at the very beginning. We just you, the programmer, can set up the whatever mean, and then as the calculation goes on, the mean will move to there, or there. Alright, so the modeling of the perceptron is actually coming from the biology of actual neuron, and this is neuron, and I assume like everyone is aware of neuron, and this is dendrite and axon terminal. What it does is it receives input through the dendrites, and that's the cell nucleus, and then it propagates the signal to the other end. And at the other end, there's another dendrites there, another dendrites receiving the signal again, and then there's another axon terminal. And in this model, in actual biological neuron, the output is several of the branches. However, when we model this, we are gonna simplify a lot. So there's a cell here, the cell nucleus here, and then just say a couple of branches that are receiving our input data, and then it's just gonna output one of them, just one value like this. So we are like chopping out all unnecessary branches. That's just, we are modeling just a couple of them, and then there's big circle here, and then we chop out everything, and then just that's one signal just like this, and that's it. So now we know this perceptron model in our software world is not an actual neuron. It's just a bunch of mathematical operator. So let's look at this. We have these three inputs in this example, and then so now we have this model neuron. In this example, we have three inputs. And in the cell, what we're going to do is we're going to multiply the weight value to each input, and then sum them up, and we're going to add bias, and then we're going to have activation function, and this output of the function is our actual output. And the reason why we have weights here is because we want to give more weights if this input is more important. And say if this input is very trivial, then we want to make this W3 as 0, so we can just ignore it. But before the training of the weight vectors here, we don't really know which input is more important or trivial. But anyway, before we talk about the training, let's wrap up this mathematical notation. So this V, the summation of wave vector and input vector, which is just dot product, and then add bias, and it's called logit in TensorFlow. I don't know, other libraries calling it as logit as well, but I'll just name it as logit. So V is this notation, and if we can simplify this, we can make it like this. Or another way of doing it is we can write it like this. Oops. Actually, I'm gonna call this one as W0, because this is bias. It doesn't really matter. I'll just call it X0. So with bias always in it, we can make it like this: 1, X1, X2, and then W0, W1, W2. Oh, there's there gotta be an X3 there. So we can just make it X x dot w. So this can be another way of expressing v, and we just need to put this logic value into an activation function. The very simple activation function. Alright, now we are going to talk about some activation functions. The first one is the step function. Step function could be the most simplest one. Say the x-axis is your logic and y-axis is the output of your neuron, and the step function would output like this, which is just like your output is 1 when v is equal to or larger than 0, and 0 otherwise. And since this is kind of blunt in this area, so what we can do is making a little bit more smoother function, and that is called sigmoid. Something like that. Another type of activation function is hyperbolic tangent function, and it's just like a sigmoid, but it spans from -1 to 1, and that's the only difference. And then ReLU function is there, and it is always 0 if your logic is less than 0, and it goes up forever. From now, we're going to talk about some logic gate implementation using a perceptron. And let me go over a simple logic gate. Say we have two variables like x0 and x1. And then if we draw this in two-dimensional plane, say these are red and that one is blue, then 1, 1 is here, blue, and then all the other points are red. These are x1, x0 and x1. So by just looking at this 2D distribution, we can just draw a line, and then what we can say is everything right to this green line is blue region, and everything left to this green line is red region. And it's called linear separability because we can just draw a line and we can separate two classes. So how could we implement this using a perceptron? So let me draw one cell nucleus first, and that's our x0 and x1. Let me actually let x0 as our bias. Then we'll need x2. So we're gonna have to change everything like this: x1 and x2, x1 and x2. Then if we set our weight like weight 0 is going to be -2, and weight 1 is going to be 1, 2 is 1. And our activation function will be simple like this. And then that's it. So let's check. So when x0, x1 and x2 are there, and our x0 is always 1 because it's biased. Let's check. So x1 is first 0, 0, and v is then going to be -2 because weight is -2, 1, 1. So -2 plus 0, 0 is going to be -2. It's going to be 0. And then next one is 0 and 1. So weight vectors for x1 and x2 are always 1. So it's going to be -2 plus 1 is going to be -1. So activation will be 0. And same here. And eventually when -2 is multiplied and they are 1, it's going to be 0. So it's equal to 0, so we're going to have 1. So we can classify whether, well, it's AND gate, but we can classify this AND gate result. So when x1 and x2 are 1, it's blue. So we can classify these inputs. The idea of the OR gate is the same. We can draw the green line like this. So let's also draw a perceptron model for OR gate. There's always our bias there, and x1 and x2. And our weight vector here this time will be -0.5, and then 1 and 1. We multiply this -0.5, it's going to be -0.5. It's less than 0, so it's going to be 0. 0.5 plus 1 is 0.5, so it is going to be 1. Same, 0.5 is going to be 1. -0.1, and it's going to be 1.5, so it's going to be 1. So as we can see, we can also output the correct answer. Oh, what was that? That was blue. So we can output the correct answer for NOT gate is also pretty simple. Since we have only one input for NOT because it's just inverting the sign. So NOT gate is pretty simple. So say we have only one input, x1. It's 0 or 1 either, and NOT is going to be just 1 and 0. And there's really nothing too much to talk about linear separability because it's trivial. Because 0 goes to 1 and 1 goes to 0. So and you can just draw a line like that. And the perceptron model for the NOT gate is just by adding a weight vector -1 to your input. And it's just your NOT gate because say when your x was 0 and it's gonna invert. V, your logic gonna be 0. So your output will be, let me draw this again. So it's 0, so it's going to be 1, and if it is 1, it's going to be -1, and it's less than 0, so it's going to be 0. So as you can see, we are inverting this 0 to 1 and 1 to 0. And XOR gate is a little interesting and a little complicated. So the point here so far is that by finding out the correct weight vectors, you can implement the logic gates. And for now, let me leave this XOR gate as a homework problem. So the sort of hint that I can give is we only need 3 perceptrons. Actually, it's not implementable by using 1 perceptron. So we're going to have x0, which is bias, x1 and x2, and these will be all fed into each perceptron, and here as well. Then by finding out the correct weight vector, we can implement where is it? We can implement the correct XOR gate for using these 3 perceptrons. And I'll leave this as a homework problem. So far, we've been talking about the logic gates using perceptron by guessing the weight vectors in a very clever way so that we can get the proper output for AND or NOT and XOR gates. However, if we don't really know, there's limited time for us to guess the correct weight vectors, then we can really use the neural network like in this manner. So there is sort of a specific rule for updating the weight vectors of the perceptron, and it's called perceptron learning rule. And this represents the next weight vector value, and then this is current weight values, and this is the change of the weight vectors and weight values. And this delta W is expressed like this, and eta here is learning rate, and then y minus y hat is the error. So y, just simple y, is our actual y value or desired y value, minus y hat is the predicted one, like the output of the perceptron. And this is error. And xn is just current input that caused this error. Let me go over a very simple example. So for this example, let me set eta as 0.5, and since we don't really know what is correct weight vector, let me initialize weight vector as just 0, 0, 0. And this is 3-dimensional because I want to put the bias at the very beginning of our input. So for example, this blue point, say this is A, and is at 0.1, and it's labeled as blue, and let's set blue as label 1. And this point B is at 1.0, and let me set red as -1. And then let's also set the activation as before, 1 if v is larger than or equal to 0, and 0 otherwise. So our input with bias is going to be 1, 0, 1. And our wave vector is going to be just 0, 0, 0. And the logic value is going to be just 0 because, well, 1 times 0 plus 0 times 0 plus 1 times 0 is just 0. And actual label is 1. And since it is 0, so we if we think about this part, and it's just going to be predicted the 1 is 1. So there's no error, luckily, as coincidence. So dw, delta w, is eta times error times input. Now our eta was 0.5 and error was 0 and input was 101, and this one is just going to be 0, 0, 0. And same idea here, 1, 1, 0, because bias is 1 and 1, 0 is here, and wave vector is again 0, 0, 0. It's going to be 0, and actual label is -1, and we predicted it as 1. Then error is going to be y minus y hat, so -1 minus 1 is -2. So our delta w will be 0.5 -2 times our input 110. So it's going to be -1, -1, 0. So our total delta W is going to be -1, -1, 0. So our next wave vector is going to be -1, -1, 0. Because we added this one to the previous wave vector, which was 0. So next wave vector is going to be -1, -1, 0 because of this. So we had a 0, 0, 0 this part, and then we have delta W as -1, -1, 0. So we're just adding it for the next wave vector. So our input is not changed, so 1, 0, 1, 1, 1, 0, and our wave vector will be this time -1, -1, 0, because we have updated it, -1, -1, 0, and y was, let me see what was, so a was 1, b was -1. So let me then calculate this. So v is going to be -1 plus 0 plus 0, so it's going to be -1, and since it's less than 0, it's going to be -1, and v here is -1, -1 plus 0, so it's going to be -2, so it's going to be -1. And now error this time here is 2, and this time this one is 0. So let me calculate the delta. So delta W is 0.5, and my error this time is 2, and input was 101. So delta W, this one will be 0.5 times 2 is 1, so it's just 101. And delta W here is just going to be 0 because error is 0, so everything will be 0. And next to W is current W plus delta W. and the sum of delta W here is 101, so I'll just add 101 to the previous weight. So -1, -1, 0 plus 101, and this is going to be 0, -1, 1. Okay, then let's go to next iteration. This time the weight vector is going to be -0, -1, 1, 0, -1, 1. And again, x is now not changing, it's still the same. 1, 1, 0. And our vector, the label for this one is 1 and -1. It's not changing. So let's calculate the logic for A. It's going to be 0, 0, 1. And this one is going to be 1 times 0, which is 0. And 1 times -1 is -1 plus 0, because 0 times 1 is 1. So, and now 1 is larger than 0, so our prediction is going to be 1. And -1 is less than 0, prediction is going to be -1. So there's no error. This dw is going to be 0. We don't have to update next one because it's right, because we have found the correct weight vector, which is 0, -1, 1. And if I draw this, it may look like this. So that is bias, the first one, bias is just 0. And the first one, the coefficient for x0, x1, and there's x2. So v is now it's like this: -x1 plus x2. That's our v. And our decision decision boundary was at 0 because activation function splits the decision based on 0. So we can set v as 0. So v is going to be -x1 plus x2. Then x1 or x2 is x1. So it's just this line. So this is our decision boundary.